Hello student, welcome to today's session. So today we will be discussing one important question based on the topic of alkyl halides, that too pertaining to SN1, SN2. In fact, the question which I am now going to discuss it with you is a more than one choice question. This is a question which is meant for JEE Advanced, but those who are appearing for JEE Mains and NEET examination also get benefited from this particular discussion because the problem in many ways is going to discuss many aspects of SN1, SN2, SNI, leaving group, and things like that. So make it a point. The video may go in length, but after the seeing into the video solution of this particular problem, you feel benefited and you feel strengthened with the topic. So here comes the question. So in many ways, many students ask me often that they are not able to get the organic. They have done the syllabus, but now they are not feeling confident about the organic part. So I just always say that organic is just like a mathematics. More you practice, more you learn. And any given organic reaction can, or any organic problem becomes a little tricky and difficult once a stereochemistry get involved into it. Just like in this question, if I just would rule out the organic stereochemistry aspect out of it, the question is very easy. But once I engage the stereochemistry, it becomes a little tricky one. So you could very well see that in this, there are two reactions given. And I'm starting with saying this thing very first, that it is a more than one choice question. Okay. So here you are being given two compounds, two reactions, and the starting material for the two reactions is the same, and they are just like an enantiomeric pair, because if you could see first and second, these are just non-superimposable mirror images of each other. So both of these are enantiomers. Now these enantiomers are being treated with different reagents in the first step, but in the final step you react with the same OH negative. So here also is the OH negative, here also is the OH negative. Now let us first discuss, and these are the options given to you, A, B, C, D, and you have to select. It may have a answer more than one choice. So let's start with the discussion. Now I always say to my student that first, eh, during any organic reaction where you are not very clear with the aspect of stereochemistry, or even if you know the stereochemistry also, I always advise first to just do the reaction in a basic level, not engaging the stereochemistry. What I'm trying to say here is that first see what this compound is. This is ethyl part, this is methyl part, and this is the carbon, which is the chiral one. So you have CH3, CH2 on one side, you have CH, this is the CH, and one is OH, another is methyl. So basically you are having a one of the configuration of 2-butanol. So the starting material is 2-butanol. Now 2-butanol is in effect, in a way, is a alcohol. So I'm writing just a alcohol, and this alcohol is being treated with thionyl chloride. Now we would be doing the mechanistic viewpoint about it, but let me write the shortcut about it, that whenever you treat thionyl chloride, alcohol with thionyl chloride, not engaging any stereochemistry aspect, we simply would say this is the simplest of way to remember it. What do you get here is alkyl halide, and SO2 would leave the reaction mixture, HCl gas would leave the reaction mixture. This is one of the way of making alkyl halides starting from the alcohol. So basically A1 is your alkyl halide. A1 is your alkyl halide. Now we have to check it whether it is going to take through uh, what configuration or what stereochemistry aspect would engage into it, because treating thionyl chloride can be of two ways. Treating alcohol with thionyl chloride happens in two ways: with pyridine, there is a compound which engages the stereochemistry aspect, and without pyridine. Here the pyridine is not mentioned, so we will be doing it without pyridine, and we'll see how the stereochemistry engages with it. Now the last part is alkyl halide treated with NaOH or OH negative. So basically this is a nucleophilic substitution reaction, which in a way I may say it has to be SN2, and seeing the viewpoint of the reaction, so you would get the alcohol back. So basically you are starting with the alcohol, you would get back the same alcohol. Now the point is, the examiner wants to know that do you know whether you are going to get the same configuration or different configuration of the alcohol. So one view is this. First, on a very basic level, you have to understand it this way, that you have started with alcohol, you treat it with thionyl chloride, you get a alkyl halide, you again treated it with OH negative, you get back the alcohol. Now the point only here is that the whether you are getting the same configuration or the different configuration, this is what they wanted to check in the question. Okay, so this is one thing which you should know about. Similarly, if I go for the second reaction, I haven't yet completed with the mechanistic viewpoint. We will be doing it in a while. So this is the another configuration they have taken, the mirror image of the starting material. This is again the butanol 2. So here you have again the same compound as butanol 2. This is the butanol 2 and this is being treated with, this is chiral, but one of the stereoisomer of this has been taken, one of the configuration of it has been taken. Now what is this compound? This is what you call it as tosyl chloride. Now what is tosyl chloride? Tosyl chloride is um, paratoluene sulfonyl chloride. This is tosyl chloride. We generally say this entire entity is written as TaCl. So first you have to see into the fact that what do you get when you treat alcohol with tosyl chloride? What you are able to get out of it. So basically here what is the viewpoint? The lone pair of alcohol is going to attack this, is it okay, and throws out the Cl negative out. So basically you end up getting a compound which we may say it like this, that you would get this part, you would get this thing, you have attacked the tosyl chloride and Cl negative has gone part and you get with ROTS. This is what you have to see into it. You are going to get the, or let me write it once more for you. As I said, this is tosyl chloride, and in the tosyl chloride, if I would mark it like this, that you have treated it with alcohol, you have treated it with alcohol. So alcohol's lone pair attacked this part, this went up. So what you get here is something like this. This becomes O negative. Here you have Cl, and you also have attacked this part, and this would get a positive charge here, and along with it this is the part. Now you would be losing the H positive. H positive goes, this goes back, throws out the Cl negative. Cl negative goes out with the H positive, and the place where you have attached the chlorine, now you would get the alkoxy part. You would get the alkoxy part. You would get something like this. This is the part you are going to get. This is the alkoxy part. So what basically we are trying to say here is that you have treated with this tosyl chloride. What here do you get? You are going to get, if I just would mark this as entire of this part as ROH, if I would say this is ROH, this part entire is R, so you are able to get, here tosyl part. Instead of H, you would get the tosyl part. Now again what you are going to do is this OH negative is going to attack this R and throws out this tosylate. This tosylate is a good leaving group and you get back the alcohol. So again the examiner is asking the same thing. Now what I did in the last step, I did it little fast. So here the next part is they are treating it with OH negative. This OH negative then attacks this. Here you have a carbon, this R part is the carbon, and this goes out. Now why it goes out is a very important part, because this is a very good leaving group. This is a very good leaving group. Leaving group is that entity which leaves the reaction mixture very rapidly because it is quite stable because of the resonance. This is a good leaving group. Tosylate is a very good leaving group. So along with it, I should write here is, this is the part which we have written. This is a very important leaving group which we are saying it as tosylate. Tosylate increases the rate of SN2 reaction. Being itself is a very good leaving group. There are few more which we can add here. Just like this particular compound, we named it as para-toluene sulfonyl chloride. Similarly, you have methane sulfonyl chloride. This is messy chloride. Now here, if in case you treat it with ROH, again the same viewpoint can happen. The Cl goes out and you would get a compound like this. This also is being used in loss of HCl. Now this, if in case, is being attacked by some other nucleophile, this nucleophile attacks here, this goes out. So this, the entity which is going out, is called as mesylate. This also is a very good leaving group. Since why is it a very good leaving group? Because it's a very stable conjugate base of a very strong acid, which we call it as methane sulfonic acid. So this is methane sulfonic acid, which is having a pK value less than 1. So it is quite a strong acid, quite a strong organic acid, stronger than carboxylic acid. And since it's a conjugate base of that acid, so it is quite stable. So any stable anion which leaves the reaction mixture is a good leaving group. So this entity is called as mesylate ion, which is also a very good leaving group. Another one which you can add into your knowledge bank is Triflate. That is also very important. This is, if I just instead of this methane here, if I just would attach 3 fluorine groups which are electron withdrawing, this we call it as trifluoromethane sulfonic acid. Again, in this case, if you treat it with ROH and this goes out, and you would get something like this. Again, it would increase the nucleophilic substitution reaction. If in case it was being attacked by some nucleophile, the leaving group which you are going to get here is R nucleophile. Along with it, what you are going to get here is, shall I write it here? So you would get something like this entity. So you shall be getting, this is called as triflate. This is also said as super leaving group. Super leaving group. So let me cut short the long story short, and what basically we are getting here is where we were. So we are here somewhere. So basically, I just have referred here is a tosyl chloride, mesyl chloride, and triflate ion. That three entities are a good leaving group. They are generally being placed into the alcohol so that they can speed up the nucleophilic substitution reaction. Any weak nucleophile even can throw out this tosylate or mesylate or triflate. Now, basically, this second and this B2 is again alcohol. So, if I haven't used much of the stereochemistry aspect till now, I can address many options of this particular question if you have read it well. So, if I would say, the first option, they said that A1 and A2 are constitutional isomers. So these two are not isomers. As a matter of fact, constitutional isomers are structural isomers. Um, Here, what we did get here is alkyl halide. Here you get a tosylate. So basically, these two are not the same isomer. So the first statement in itself is a wrong one. Now they said 1, 2, B1, B2 have same IUPAC name. Since we are not sure about that yet, we haven't discussed that part, that whether these two are same configurations or different. And similarly, these two are same configurations or different. But this is for sure, both of these are the same alcohols. So definitely they would have the same IUPAC name. So two options we have cross-checked. Now to check the C option, we actually have to go into the stereochemistry aspect. Otherwise, we would not be able to fetch the right answer. To get that, the video would go in a bit more length. Let me discuss that aspect in regard to the stereochemistry. So in regard to the stereochemistry, you have to see one thing first. This is what you call it as Fisher projection. This is, they have given the Fisher projection. Now, how does you see the Fisher projection? The vertical and horizontal lines, whatever you have, what the groups present on the vertical lines are actually going into the plane of this slide. That this ethyl is going into, and this methyl is also going into the plane of the board. And the carbon which we have referred here at the center is actually in the plane of the copy or plane of the slide. And this OH, the groups on the horizontal line are coming outward. So make it a point the groups present on the horizontal line are coming outward and the groups present on the vertical line going inward. This is what first you have to see into it. And this, what I have shown, is a Haworth projection. Now, how do you get into the viewpoint of the three-dimensional stereochemistry part if I just would want to see it like this, in this form, if I want to see it? Now, the simple fact here is this methyl and ethyl are going into the plane of the copy. Now, those groups which are going into the plane of the copy, just take it onto the simple line. Just ethyl and methyl, place it onto the simple line. And this OH and this H are coming towards you. Now, if they are coming towards you, how to see it like this? You just have to make a line here, just like this arrow. This is a shortcut I can play. There are many ways to make the facial projection into 3D in this way. There are number of ways, but in this small video I am just going to tell you one way. The one way is that if you will place yourself here, the arrow, and position yourself towards these two groups, such that these two groups seems like in a vertical line. These seems like in a vertical line. You placed yourself here and you are watching this two groups. You are watching from the angle or from the viewpoint where this group is coming towards you, this line is coming towards you, and the dotted line, this dotted line is going into the plane of the copy. Between these two groups you are seeing, such that this would become a vertical line. This is what I am referring. This should become a vertical line, and the horizontal line would become this one. This becomes the horizontal line. So what I'm saying is, here you have OH and here you have H. Now let me do it in the reverse way. The reverse way is, if you have this sort of a structure, how do you see? You have to place your body, or you have to see it from here, such that this group which is coming to outward and this group which is going into, just place your body or your eye in the center of that and see it this way, that this line becomes a vertical line and this would become a horizontal line. This is the best way to see the 3D molecule, or to convert 3D into Fisher or Fisher into 3D. So this is one way. Now what you are able to see here is, the examiner has given us the starting material as, the one starting material they have given us is this one, where ethyl is here. If you could see, ethyl is here, methyl is here, and this is OH and this is H. This is the projection number 1. And the second structure in the reaction they have given, they just have swapped OH with H. So if I just now would place onto the 3D projection, it would look like this thing. So as I said, methyl and ethyl, whatever is in the vertical line, just place it onto the simple lines, and OH is here, H is here, and see it from here. If you see it from here, you would see the Fisher projection like this. And similarly, here the OH is here, H is here, ethyl and methyl. And if you see it from here, you would see the Fisher projection like this. So these are the two starting material you have. These are non-superimposable mirror images of each other. And these are enantiomers. If this is dextro-rotatory, this is levo, or if this is levo, then this would be dextro. What does it mean? If any of these rotate the line by plus 20 degree, other one is going to rotate it by minus 20 degree, which we can not tell you from the theoretical aspect, that the value which we are going to get is through the polarimeter. Now these are the two starting material. Now let me come into the discussion of the first reaction. In the first reaction, what we have said, that this part first attacks this thionyl chloride. If we go into the mechanistic viewpoint of how alcohol reacts with the thionyl chloride, that is what you have to see now. So here what you are going to see here is this attacks. I yet not have engaged the stereochemistry. We would be doing it with the stereochemistry aspect also. Now see, this is what you are going to get, and here you would get the positive charge. These are the lone pairs of the electrons of oxygen which attack the sulfur, and now this comes back, this goes out, so that this oxygen would not get the positive charge, and along with it this Cl negative also goes out. Now what you would get is somewhat like a ester type of a thing, sulfonate type of a thing, chlorosulfonate type of a thing. This is what you have got during this reaction. Now if I just would engage, because this is the R part which was the having the stereochemistry angle into it. What that stereochemistry angle was, that we have just have said that here you have OH, here you have H, and this part was methyl, and this part, sorry, this part was methyl, and this part was ethyl. This is what, and this is the entity, because at present nothing has got attacked onto the, nothing has got attacked onto this carbon. The carbon which is having the configuration is not being attacked by anything. The attack happened at the OH part, so the configuration would retained, would be as such in the reaction. So what I'm trying to say here is that after the reaction, what basically do you get here is this part would remain the same one, this is going to remain the same one, and here you have ethyl, methyl, and H. This is what you are going to get. Now basically, now you have to understand two aspects into it. During this reaction, what gone out is HCl, and during reaction of this with thionyl chloride, we are going to do the reflux, and during this refluxing, this HCl which is being produced because of the high temperature of the reaction, this keep on going out as a gas, this keep on going out as a gas, as long as you don't add pyridine into it. Now what is the role being placed by pyridine, that also we are going to answer in a while. So what I'm trying to say here is that what is the next viewpoint about it. So you have a compound made like this. Just see it with me. This is called as nucleophilic substitution of the type internal. What I'm trying to say here is that the HCl went out of the system. HCl went out of the system. Now what you are basically going to do is this part is going to attack onto this carbon, and this bond comes here. These two electrons come here. As a process, what you are going to get is RCl along with the evolution of SO2 gas. SO2 gone out. Now this what you call it as, this is called as nucleophilic substitution of the type internal. Internal nucleophilic substitution. Because SO2 is a good leaving group being a gas, and Cl is a only entity left to bring about the reaction. So now if I just would place, instead of this R, I just have placed the configuration. If I just would place the configuration, what is the configuration? The configuration is still the retained one, still the retained one. I haven't yet have done anything onto the part of this carbon. Now see here. Now this is SO2 and here you have Cl. So this Cl is attacking onto this carbon right from the place from where the leaving group has to depart. What is the leaving group? Leaving group is these two electrons. These electrons come here and this attacks at this position. Are you able to get it? I think I am making the point very right. So what I am saying here is this Cl negative attacks this carbon, this goes here, and SO2 goes out. So this is what you call it as nucleophilic substitution of the type internal, where the attack has happened from the same side from where the leaving group is departing, from where the leaving group is departing. So here, if I would just add one more thing into it, that basically, just hold on. Basically, if I just would add another viewpoint here is that during this reaction, what entity do you get here? You are going to get the same compound with the same configuration, that is with the retained configuration. You would get methyl, you here would get the H, but here you are going to get the Cl. So what you are able to get is the retained geometry. If pyridine is not there, you would get the retained geometry. Now this reaction has happened without the presence of pyridine, and this is called as nucleophilic substitution of the type internal, where the leaving group which is departing is also behaving like a species from where the nucleophile is attacking also. So attacking reagent, that is the chloride ion is attacking and leaving group is departing from the same side. But unlike if it had happened in the presence of pyridine. Now what is pyridine? Pyridine is a nitrogenous base, heterocyclic aromatic nitrogenous base. So if the HCl, if the solution is having along with pyridine, so then the HCl is not going to go out as gas out of the system. In the presence of pyridine, you are going to get a inverted geometry. Now how do you get that? So you are going to get this part and this chloride. Now in this case, what might have happened, that you have this entity with you, CH3 ethyl. Here you have what you call that as to be hydrogen, and here you had been SO2 and Cl. This is what you have. Now, if in the system you have the availability of chloride ion, then chloride ion would have attacked from the backside. And chloride ion on attacking from backside have given you a inverted geometry. The one which you are getting now would be having a inverted geometry. Now you would have got chloride on this side, ethyl and methyl, and H on this side with the loss of SO2 and Cl negative. So this is very, very important, that if you are being said, that if you are being given a compound like this, this is methyl, this is the starting material they gave. If they are giving it with thionyl chloride, or if they are given with thionyl chloride in presence of pyridine, the answer would be different. Here you would get the retained geometry, the OH get changed into Cl, and the retention is there. You would not be getting anything other than this. And here you would get ethyl, methyl, and here you would get Cl, and here you have. So here you got retained geometry, and here you would get inverted geometry. Is it okay? So this always you have to remember with that thionyl chloride treated with pyridine, you would get inverted. Here you would get the retained geometry. So this in a way shows that I got this compound as the final product. Now one more thing to add here. We yet not have completed with the answer. So we started with this compound. What was this? Ethyl methyl OHCl. The video went in length, and you treated with thionyl chloride, you got the retained geometry. And the last part is OH negative. Now this OH negative has to happen through SN2, nucleophilic substitution of the order of second order, where there is total inversion of configuration. That during, I just would write it like this, that if you have a compound somewhat like this, that if I just would write it in a fashion that this is the leaving group which you are going to throw it out, and this is the tetrahedral you have with you, and something like this, that if OH attacks from the backside just like this, then you would these three groups R1, R2 and H, these three groups would come in one plane during this, and this would look like somewhat like this. And this is the leaving group which is going out, Cl, and this is the incoming nucleophile which is coming to attack it. This is the transition state which you would get for a SN2 mechanism. During SN2 mechanism, it is just like a spokes of the wheel, and these are this OH and Cl attaching with carbon is just like the axis of the wheel, and these just behave like the spokes of the wheel, isn't it? It is a pentagonal bipyramidal type of a structure in the transition state, and thereafter the Cl goes out and the OH got attached with it. So basically what you happen to get as a final product is you would get the OH on this side. It is total inversion of configuration. So you started with this one, and this is inverted product. During SN2 you would get the inverted product. So basically This now you would get as OH on this side, it is inverted product you are going to get. And this inverted product which I just have shown, that Cl would get swapped because it got attacked from the rear side. The rear side attack has happened and Cl goes out, and the OH group just attaches itself right in opposite direction to the Cl group. So you would get this compound. So the final product which you received in this particular reaction is OH, this is methyl, and this is ethyl. And to me, this is structure number 1 itself. This is structure number 2 itself. Let us check this out in the options. So we got the B1. We just have understood the B1. B1 happened to come out to be OH. This is ethyl. This is methyl, and that is exactly the second structure. Now we have to go into the second part of this reaction, which is not a very difficult one. For that, we have to understand one aspect. What is that aspect? Is you have OH group here, and we started with, just hold on, we have this as a starting, as a second compound is this one. So OH, ethyl, and this is methyl, and this is H. How does it look like? This would look like OH on this part, H on this part, just like the way I have just told you how to make the Fisher projection in a speedy way. So if you see it from here, how does it look like? So this would look like OH on this side, H on this side, and this ethyl and methyl on this side. So exactly it is the second structure. Now thereafter you treated it with tosyl chloride. Now if you treat entire of this moiety as R part, this is the R part, and R part, so you have ROH, and you have to treat it with tosyl chloride. So what exactly would happen here? The this OH negative would attack this and throws this out. So basically you would get a tosyl getting attached onto the same side, to OTS get attached here. So there is no change in the configuration, of the chiral center, because this carbon is not being attacked by the tosyl chloride. In fact, this lone pair of oxygen actually has attacked the tosyl part. So the configuration get retained. So this is retained configuration. Just like in the previous question itself. This is the retained configuration. Now, what next you have to do it? You have to attack it with OH negative. Again the SN2. So OH negative would attack from the rear side to the group which OTS has to go out of the system. So it is exactly the same. Here again you would get the inversion of configuration. So how does this inversion of configuration would be shown to you? It is very simple to show it, that it would be exactly the opposite to what we have started with. So if I would say here that we started with this, so here you would get OTS, this is ethyl, methyl, and H, and thereafter what you have done, you have treated with OH negative. So you have to, this OH negative attack this carbon, this OTS has to go out, and the configuration would be exactly the opposite, or it is the retained. Now you would get the inverted geometry of feature of SN2 reaction. So what you basically get is this methyl and this is H. So now you could see this is exactly the same configuration as 1. So to do, just to see, or just to check the C option, we have to go into such a length. So, but anyhow, it is always good to have the discussion, because that in a way clear many things. So here you have methyl, and here you get OH and this H. Now what they are saying, B1 is 2, which is perfectly right, and B2 is 1, which is also perfectly right. B2 is 1, this is 1, and this is 2, which is perfectly right. So this option in a way is also correct. Now we are left still with the last option. Now what the last option says, the product of following reaction, that is this reaction, is contain 1 to B1 B2. So in a way, one is exactly the same as B2, and B1 is exactly the same as 2. So these are same in a way. So B1 is 2 and one is B2. So these are same, exactly identical. So what they are saying is this reaction. So here you could see here no stereochemistry is being shown. And who is the nucleophile? Water. So this is a case of solvolysis. Do you know it? It's a case of solvolysis. The starting material did not have any stereochemistry given. So this particular compound has a chiral center, so that is not being shown to us that whether it is they are starting with one specific pure enantiomer. They are not mentioning that. They are simply saying treat it with OH negative. So what does it simply would say to me or to you? Basically, it's a case of solvolysis. Solvolysis is a case where solvent itself start acting as a nucleophile. Solvent itself start acting as nucleophile. Solvent itself start acting as a nucleophile. That's the case of solvolysis, and that always happens through SN1. That is through the carbocation formation. So we will be saying that first what step would happen in this case is during this mechanism of SN2 SN1. The first step which we happen to say here is, sorry, this is Cl negative Cl. Have I shown Cl? Yes, it is Cl. So first step is Cl negative goes out, leaving behind a carbocation, and this carbocation, if I would show it with stereochemistry, they are showing it somewhat like this. Just stay with me. So what they are showing is something like this, that you are being given this compound, ethyl. Let me take methyl H, and this is Cl. This goes out in the first step, that is the carbocation formation, and this is the slow step, and you are ending up getting a carbocation which is planar. This is the carbocation which we received, Me, and this is H, and this is the positive charge. This is planar, and Cl negative went out. Now this planar carbocation which I have just shown, this is the planar carbocation which we have in the vertical direction. I have shown ethyl, methyl, and H, and this is having a positive charge, and this is the perpendicular p orbital which is vacant. Now this is to be attacked by water as a nucleophile, which can attack from this side also, and this water can, because it is planar, it can be attacked from both sides, both the directions. So in a way what we are saying is that you may either receive this one OH here, and this is the H, and or you can get this one. But generally we say inverted product is little more than the retained one, because during the inverted product the attack is from the rear side to the carbon chlorine bond. So this is the configuration which we have started with. First Cl negative goes out and you get a carbocation. Now nucleophile, that is the water's lone pair can attack from this side or from this side. So major attack would happen from this side because the leaving group is going from the other side, just to have remove out the steric repulsions. So what basically you end up getting here is, I just have drawn in a hurry. I should rub this part. It should be shown in the way which we have started with. So what do we get here is something like this, exactly the same as we have shown here. Let me show it here only. So you would get something like this. So methyl and ethyl, methyl, and here you have H, and here you will get OH, or you would get this one, ethyl, and here you have methyl, and here you have H. So both of these are formed, that is retained geometry as well as inverted geometry. What we are trying to say is that we will be getting the same. You can get this one also, and you also may get this one. And there can be depending upon the type of other things in the reaction mixture, but generally we say inverted is a bit more. This is inverted is bit more than the retained one. That is why there is not complete racemization. On to this particular question or this particular discussion, I have already made a video which is there in the playlist of last year DCD problems, you can refer to that. So this question had been in a way a bit more lengthy, but having said that thing, I still would feel that you must have got the uh, understanding of this particular problem. So I have to check the C option now. So what is there in the C option? The product of this, yes, you definitely would get during this reaction, you would get either this or this. Both of these things are being formed, and they definitely got formed, but that's a different story. That would it be equal or unequal? If it had been equal, then it is complete racemization. If it is unequal, this is partial racemization, and generally we say inverted becomes a bit more than the retained one. Thanks a lot. I hope you have liked this problem, and in case you have found it well, do comment. It would really motivate me, and the question had been more than one choice. Thanks a lot. Have a nice day. Stay safe and take good care of yourself.